The third case is this. What is the third case? Log of y I equals to alpha plus beta xi plus ui. Log of yi equals to alpha plus beta xi plus ui. Okay. Now, if I apply the interpretation of model 1 here, then what I can write that for a unit change in xi, for a unit change in xi, expected value of log of yi changes by beta hat amount. Okay. When x changes by 1 unit, log of yi changes by expected value of log of yi changes by beta hat amount. That is the interpretation. But as I said, understanding change in log of yi is little difficult, because what we want is we want to get the changes in yi. So, this is equivalent to e to the power of beta hat amount change in yi. When x changes by 1 unit, y changes by e to the power beta hat amount. Okay, e to the power beta hat amount. Now, for small beta hat, e to the power beta hat equals to, actually e to the power beta hat is almost equals to 1 plus beta hat. Okay, 1 plus beta hat. For example, let us say the beta hat is actually 0.06. So, this implies e to the power beta hat equals to 1.1 plus 0.06 equals to 1.06. Okay. So, that means what we can say, for a unit change in xi, expected yi value of yi changes by 6%. So, when beta hat equals to 0.06 in this type of model, when you estimate log linear model, when beta hat changes by, when xi changes by 1 unit, then your yi will change by 6%. Previously, look at the difference. Here, when your x is log, what I am saying, for 1% change in xi, yi changes by this much, beta hat divided by 100 equals to 0.05. So, this is percent, this is unit, this is just the opposite. For 1%, for a unit change in xi, y changes by 6% if your beta hat equals to 0.06. This is the third model. What is the fourth model? Fourth model is log-log, log of y I equals to alpha plus beta log of xi plus ui. And what is the interpretation of this model? To understand the interpretation of beta hat, this is the most familiar, one of the most useful econometric model is log-log, okay? And I will let you know what is the interpretation of, this is the equation, what is the interpretation of beta hat here. Now, what I am saying, differentiate this with respect to xi, what you will get? If you differentiate this with respect to xi, you will get 1 by yi into dy dx equals to beta into 1 by x. And if you multiply both sides by xi, then you will get xi by yi into dy I dxi, which you can write as dyi by yi divided by dxi by xi. Okay. Now, if you look at, can you recall this relationship? Suppose this is my demand function, yi is the demand for the ith product and xi is the price of the ith product. Then in this context, this is nothing but this is equals to your actually beta hat. So, in this context, as you can see, beta hat is nothing but the price elasticity of demand. That means, for 1% change in xi, y changes by beta hat percentage. Okay. So, that means here the interpretation of beta hat is here a direct measure of elasticity, direct measure of elasticity, direct measure of elasticity when your model is log-log. This is a quite interesting and useful model. Whenever you are interested in estimating direct elasticity, then transform this model into log-log, and that log-log transformation, from the log-log transformation you will get beta hat as a direct elasticity measure. Okay. So, that means I can say that the interpretation is for 1% change in xi, for 1% change in xi, expected value of yi changes by beta hat percentage. Okay, beta hat percentage. This is the interpretation of beta hat. So, these are the alternative 4 models. First model is linear, both y and x is linear, and the interpretation is simple, which you have already learned. For a unit change in xi, on an average yi changes by beta hat amount. What we did, we have tried to apply the same interpretation in all these models, and then at the end we derive the actual interpretation of beta hat in that log transform model. All right. Now, what we will do? We will take one data set and we will estimate these 4 alternative models and we will try to understand their interpretation. So, this is the data set actually. If you look at the data set, here we have a data on output, labor and capital. Basically, we are estimating a production function. Okay. These data would be useful later on also. So, this is basically a data on output, labor and capital, and we can estimate different type of production function, right. Let us first say that we are estimating the first model where both your yi and xi is linear. Okay. So, what we will do, we will estimate this. Reg output is my dependent variable output, then my independent variables are labor and capital. Okay. This is the linear model we have estimated. All right. So, how will you interpret the coefficient? This is very simple. For a unit change in labor, on an average output increases by 147 unit, that is the meaning. Similarly, from the coefficient of capital, we can say that for a unit change in capital, okay, for a unit change in capital, output increases by 0.4035 unit. And both these variables are significant, because if you look at the p values, if you multiply the p value, corresponding p value of labor, then you will get 0.002 multiplied by 100 is 0.2, which is still less than 1. So, that means both are significant at 1% level. Both labor and capital, they are significant at 1% level. That is what we have understood. So, this is the interpretation. Now, what we will do? We will estimate the log transform models. For that, we need to transform all these variables into log. So, let us say how to transform this variable. Let us say log output equals to ln and then output bracket. This is the command. So, that means I have transformed my output into log and I have given a name called log out. Log out is the logarithmic transformation of the output variable. Okay. This is the command in Stata. Whenever you want to transform a variable into log, you have to use the gen command. So, after gen you put some name of the variable. I have given log out, you can give any other name as well. And then after this, what I am saying, this is the function. I am saying this is actually logarithmic transformation. So, ln within the bracket output. Similarly, gen, let us say log labor or log L equals to ln within the bracket you put labor. So, I have created another variable which is log L, that means logarithmic transformation of labor. After that you put this gen log capital, or let us say I will put log cap equals to ln within the bracket capital. Enter. Okay. So, now what I will do? I will use the second model where x is log transform, but y is not. So, reg output, and then I am putting log labor and log capital. So, this is called Lin-log model. Left hand side is linear, right hand side variables are log transform, and this is my model. Okay, this is my model. Now, the question is, how will you interpret this coefficient? Okay, how will you interpret this coefficient? We will go back and see the interpretation. So, that means you are estimating this case when y is linear, but x is log transform. So, that means here I can say that for a unit change in for 172% change in xi, yi changes by that amount. That means how we have transformed this for a small value. For p, it is basically p by when p equals to 1, that means we can say that for 1% change in xi, your expected value of yi changes by beta hat divided by 100. Okay, unit, beta hat divided by 100 unit. Okay. Now, if you go by, that means beta hat by 100 is the unit change in expected value of y for 1% change in your xi. So, same logic will apply. So, that means for 1% change in your labor, your expected value of y will change by the coefficient beta hat is 33607. If you divide by 100, that means it would become 336.07. That is the interpretation. For 1% change in labor, expected value of your output changes by 336.07 unit, because we have derived the interpretation would be when p is small, that means we are assuming that p is here equals to 1, that means 1% change in your x, output changes by 336.07 unit. Similarly, for 1% change in capital, output changes by beta hat by 100, it would become 120.59 unit. This is the interpretation. Okay. Is this clear? That is what we have derived. Okay. For Lin-log model, if you need to interpret the coefficient, what you do? You divide the coefficient by 100, that would be the unit change in your expected value of yi for 1% change in the xi. When labor changes increased by 1%, output changes by 336.07 unit. When capital changes by 1%, output changes by 120.59 unit, and this is what we got dividing beta hat by 100, very simple. Okay. Now, the third model is called log linear model. That means my dependent variable is log transform, but independent variables are not. So, what we will do? We will regress this type of regression, reg log of output here I have given a different name. So, this is log output is named as this, and then I will simply take labor and capital. This is the interpretation. This is the model. Okay. Now, what is the interpretation of log linear model? We have to go back and see what is the interpretation of log linear model. This is the model. So, that means if you want to interpret the coefficient when your y is log but x is not, what you need to do? You need to you need to say that y changes by e to the power beta hat amount, that means e to the power beta hat equals to 1 plus beta hat. So, if beta hat equals to 0.06, so that means it would become 1.06 or 6 percentage, okay, 6 percentage. That means you multiply beta hat by 100 and that would be the percentage change in expected value of yi given xi. So, you multiply beta by 100. So, for a unit change in x, now you come here. For a unit change in lever, output changes by, if you multiply this by 100, it will become 0.65 percentage, okay, 0.65 percentage. For a unit change in lever, output changes by beta hat multiplied by 100 percentage, that means 0.65 percentage. Similarly, for a unit change in capital, output changes by this multiplied by 100, that means 0.0016 percentage. Okay. So, when your dependent variable is log transform by independent variables are not, so that means the interpretation would be you need to multiply your beta hat with 100 to get the corresponding percentage change in yi, because you are getting first e to the power beta hat amount change in y, which we do not want. Then lastly, what we need to do, we will estimate the fourth model where both are log transform, So, that means we will say that we will estimate this type of model reg, then log output, and we are regressing on log of lever and log of capital. This is our model, okay, this is our model, and this model is called log-log model, both side log transform, and if you put enter, this is the estimate. How will you interpret the coefficient? You go back to the log-log model and see this is the log-log model, log y equals to alpha plus beta log xi, and you see differentiating both the side we are getting beta hat is basically equals to then dy by y into dxi by x, okay, and as a result of which beta hat is a direct measure of elasticity in this case, okay, direct measure of elasticity. That means beta hat basically indicates for 1% change in xi, expected value of yi changes by beta hat percentage. We do not have to do anything, it is a direct elasticity measure. So, we will get direct percentage change in yi for 1% change in xi. This is the log-log model interpretation. And if you go back, now here what we see that the coefficient of lever is 1.49. What does it mean? It means for 1% change in your lever, output changes by 1.49 percentage. You have to clearly keep in mind, generally we commit a mistake, we again multiply this by 100 and say that for 1% change in lever, output changes by 149%, which is absurd. You have to clearly keep in mind that log-log model gives a direct elasticity measure. That means you do not have to do anything with this coefficient like the previous models. In previous models, we were either multiplying beta by 100 or dividing beta by 100, but here is a case where beta hat gives you a direct elasticity measure, no need of doing anything to these models. right. So, that means in this case what will happen, you have to say that for a unit change in, for 1% change in labor, output changes by 1.49 percentage. I will write this since this is, and this is 0.48. So, from this we can say that interpretation is, what is the coefficient of labor and capital beta 1 hat equals to, beta 1 hat equals to 1.49, 1.49. This implies for 1% change in labor, expected value of output changes by 1.49%. Don't multiply this by 100 and say 149%, that would be wrong. Okay? And then what is the value of beta 2 hat? Beta 2 hat is, what is the beta 2 hat? Beta 2 hat is 0.48, 0.48. That means this implies for 1 unit change in capital, expected value of output, expected value of output changes by 0.48 percentage and not 48%. So, in the bracket I am writing not 48%, do not commit this mistake. Here I am writing not 149%. So, this you have to be very careful. It is a direct elasticity measure, no need of doing anything with this beta hat coefficient, it is a direct elasticity measure. So, this is a very important topic, as I said, this logarithmic transformation. Why first of all logarithmic transformation is required, and secondly, if you transform either your dependent or independent or both the variables in log, then what is going to be the interpretation. So, this interpretation you have to clearly keep in mind. The interpretation is very simple actually, though we have derived many things, at the end of the day it becomes very simple. When your x is log transformed, when your x is log transformed, y is not, then ultimately you divide x by 100, that you divide beta hat by 100, you divide beta hat by 100, that is what we did, this you divide beta hat by 100 and get the interpretation. Okay. So, that means for 1% change in your x, expected value of y changes by this much unit, and when your y is log but x is not, when your y is log and x is not, then you multiply beta hat by 100, you will get percentage change in your y. Okay. You will get percentage change in your y. That is what you need to keep in mind, and when both are log transform, you do not have to do anything, because that is a direct elasticity measure. With this, we are closing our discussion today. Thank you.